Hey Algebra 2, here's your video for 7.1, Operations with Functions. So let's start off with a quick word problem. I promise this won't be too bad. Apple Incorporated total revenue reported in September of 2016 was $215,639,000. Their cost to produce this revenue was $131,376,000. Knowing these two facts, how much profit did they make? Well, let's go back to our basic math. We know that profit is going to be equal to revenue minus cost. So let's plug in the numbers it gives us and find out how much profit they made. 215,639,000 minus their cost, which was 131,376,000. And when we calculate that, let me find my note here, because I already did it in my calculator, we're going to find that it's $84,263,000. Let's throw a dollar sign on there. However, sometimes we don't have set values like this one. Sometimes we have math models that represent our revenue and cost. So let's look at this next one. Carol Kaufman owns a store where she sells birdhouses. The revenue from birdhouse sales is given by R of X equal to 125 times X, and the cost of making the birdhouses is given by C of X equals 65X plus 5,400. How would you express a function for the profit P? Well, as I've shown you in my other word problems, I don't like to work with a ton of words. I would rather just pull out all of my knowns. So that's the first thing I'm going to do. I'm going to say my revenue is equal to 125x. Now in a different color here, I was also given my cost. C of x is equal to 65x plus 5,400. And then, because I don't want to work with any words at all, I want to know what I'm looking for. In this case, that's P of x. I don't know. We're going to follow the same math model above. P is equal to R minus C. However, if we want to put this in function notation, we want to start working more with functions. Another way of writing this would be P of x, the profit of x, is equal to R minus C of x. Why am I including that of x part? Well, I want to start working with this idea of my unknown as part of my model. This only lets me work with numbers. This allows me to work with functions. So I'm going to do one more step here. It's not super necessary, but I do want to show you that if I were to plug in the models that it gave us, I would have P of x equal to R of x, which is 125x. I'm going to put it in parentheses. You'll see why in a minute. Minus my cost, which is 65x plus 5,400. Now, why did I put it in parentheses? Well, the problem is we have a subtraction sign in the middle. That subtraction sign causes a problem because if we don't distribute it to both pieces of our cost expression, we aren't representing the correct profit. I need to make sure that when I do this one, when I complete this expression, that I distribute that to both terms. And when I do that, I'm going to get 60x, 125x minus 65x, minus that 5,400, because I have to make sure that I am subtracting there. All right, tricky word problems. Let's go on to the main idea. So the key concept is the operations that we can do with functions when we're given two different pieces. So we can do a sum. If you say f plus g of x, it's the same thing as taking the first function plus the second function. It's giving you an example over here. If you see a difference, f minus g of x, you take the difference of the two functions separately. The product, same thing, the two functions separately. And the quotient, the two functions separately. This is really important because on the next page, we're going to start working with these two things together. But let's not get ahead of ourselves. Let's look at some quick examples. So if f of x is equal to x squared minus 3x plus 1 and g of x is equal to 4x plus 5, let's perform the indicated operation. Remember, just as I was talking about up above, if you see the two pieces in here together, all that's saying is it's the same thing as f of x plus g of x, in which case we can bring these function pieces directly down and plug them in. F of x is x squared minus 3x plus 1 plus g of x. I'm going to put these in parentheses just like I did before so I don't mess up any signs, plus 4x plus 5. From there, it's just simple addition. X squared, negative 3x plus 4x is plus x, positive 1 plus 5 is plus 6. That is my answer for f plus g of x. Next one, same thing. It's a difference, but all it's saying is take the difference separately. F of x minus g of x. This type is going to be especially important that you remember to use parentheses. Now this one, because there was a plus in the middle, it didn't matter as much because when we distribute that addition sign in, it doesn't change either of these. However, you'll notice x squared minus 3x plus 1 minus 4x plus 5. Because there's a subtraction in the middle of these two, that means I'd have to distribute that negative into both terms. So x squared doesn't combine with anything, but negative 3x minus 4x is going to be negative 7x. And positive 1 minus 5 is going to be negative 4. It does make a difference, so make sure you use those parentheses until you get comfortable with this. All right, quotient. We're going to have f of x on top in the numerator divided by 4x plus 5 in the denominator. Now, for the sake of this, I'm not going to simplify this one just for time. However, we do know how to do that from our Algebra 1 days. And if you want to go ahead and simplify, you can. The only thing that I would add to this is to say that x cannot be equal to negative 5 over 4. Because if we solve the bottom for 0, this is going to be an issue for us. So I would put that there. All right, and then f times g of x, multiply them separately. F of x times g of x is the same thing as x squared minus 3x plus 1 times 4x plus 5. And same thing with the last one. I'm not going to simplify this for the sake of time. However, you do know how to multiply trinomials by binomials. So if you want to go ahead and simplify that for your notes, probably wouldn't be the worst idea. All right, let's jump down here a little further. So a concept we visited back in chapter 2 was the idea of composite functions, where one function is nested inside of the other. So let's just take a moment to review that. If f of x is equal to 4x, g of x is equal to 2x minus 1, and h of x is equal to x squared plus 1, we're going to find each of the following. Remember, the same way that we work with all of our other functions, so too do we work with composite functions. We're always going to work inside out. So we start this one by finding g of negative 1. 2 times negative 1 minus 1 is equal to negative 3. Now that we have g of negative 1, we know it's negative 3, we're going to plug that in where g of negative 1 used to be. That kind of replaces what is inside. Now that we have that, we're going to use our f of x function. 4 times negative 3, is equal to negative 12. So our final answer for f of g of negative 1 is negative 12. And that is your final answer that I would expect you to circle. All right, let's see another one. I'm going to jump colors just because I want to. Same thing, inside out. Find f of 5 by plugging in. 4 times 5 is 20. That becomes the answer that I then put inside of the g function. G of 20 is the same as 2 times 20 minus 1, or 39. So my final answer would be g of f of 5 equal to 39. I hope this is mostly review, but even if it's not, that's okay too. It's not a super hard concept as long as you make sure that you go in the right direction there. Alright, I want you to pause the video real quick, try that last one on your own, use the last two examples that we did to help you out if you get confused, and then come on back and we'll check it out together. Alright, hopefully you paused the video to try this one on your own. Notice, same thing we did with the last two, we're going to start with the inside, parentheses first. H of negative 4 is the same thing as negative 4 squared plus 1, which is also 17. We then take that 17 and plug it into the outside function, which is f of x. 4 times 17. 17 times 2 is 34. 34 times 2 is 68. So our final answer here is 68. F of h of negative 4 is 68. And there you are. Alright, let's flip over to the backside now. So there is a second notation for the same idea. The only new thing that I'm introducing is the notation. The method that we just saw on the bottom of the last page is the exact same. So don't get confused by this. The method is the same, notation is not. Alright, so the second notation looks like this. F of g of x is the same thing as this notation. And this little circle is not a multiplication sign. If it's an open circle, that means of. Of g of x. So in number 3 here, if it says find f of g of x and find g of f of x, and are given those pieces, the same thing applies. And if you need to rewrite these to help you, go ahead. This is the same thing as f of g of x. And the second one is the same thing as g of f of x. Notice, those are the same two notations that we had down here at the bottom. We've seen this before. So this now becomes the same thing. I find g of x. G of x, because it doesn't give me a number, I'm just going to write it down. G of x is x squared plus x minus 1. I'm now going to take all of that and plug it into the f function. So f of g of x is equal to x squared plus x minus 1 plus 3. That's a little confusing because there's no numbers. Don't panic. If it doesn't give you a number, you just take that and plug it directly in where you saw your x in your f of x function. And we can simplify this too. So x squared plus x plus 2. That is our f of g of x answer. Again, I'm not changing anything. I'm just not giving you numbers to work with. Let's get away from that idea that we have to have numbers. The next one, same thing. Find the inner piece first. F of x is equal to x plus 3. Now it doesn't give me a number, so whatever f of x is, I have to plug directly into my g function. F of x, and then wherever I see an x in this function, I have to replace it with x plus 3. So x plus 3 squared plus x plus 3 minus 1. All I did was replace each of these x's with x plus 3. And then, of course, I have to simplify. This is going to be the time-consuming part, but it's not usually too challenging. So x squared plus 6x plus 9 plus x plus 3 minus 1. Simplify, x squared. 6x and x is 7x. 9 plus 3 is 12. 12 minus 1 is 11. And there is your final answer for g of f of x. Now, I think the next part is actually probably the trickiest because we've seen most of this before. All I've done is introduce new notation. This is where it gets tricky. It says for each pair of functions, find f of g of x and g of f of x, if they exist. The other thing I want to just note while I have a second here is that sometimes these are referred to fog and goth. So if you say, if you hear me say find fog or find goth, that is what I am referring to. So for each pair of functions, find fog and goth if they exist. Now, basically, I think the easiest way to do this is in the form of a table. So what I do, let's do fog down here, is I take the domain of 1. So I'm going to say this is the domain of f. And I plug it in, 3, 4, 6, 7. And what I do is if the range of f becomes the domain of g, I know that these exist. So I know that's a little confusing, but your range of f should become your domain of g. It's kind of like an inverse if you want to think about it that way. We're kind of flipping it on its head. I'm going to draw one more here. Stay with me. I know this is confusing. I promise it'll get easier. Range of g. So if I do this right, my domain of f connects with my range of f. I'm just saying 3, 8, 4, 0, 6, 3, and 7, negative 1. My domain connects to a range. Now, if I have f of g and g of f, I should be able to loop these back. Each one of these should have a counterpart in g. So my domain of g. Do I have a domain of g, an x value in my g function here, that connects to a range? Well, do I have an 8 anywhere along here? I have an 8 in the x position. I notice it connects to a 6. So this range now has a domain. We're good to go. This one, do I have a 0 in my x position? Yes, that domain now has a range. I have connected it back. I now have a domain 3. Does it have a range? Yes. Connect it back. 3, 6. And the last one, I have negative 1 becomes an 8, and I have come full circle. So essentially what we're trying to see is, do each of our ranges of our f match up with a domain in our g? So this one would be our f of g, our fog example. Let's see another one. Let's do our goth. So if we're going to do our goth, or a g of f, we need to start with our domain of g. Domain of g is going to be 0, 8, 3, negative 1. 0, 8, 3, negative 1. Now, if goth exists, each of my ranges should relate to a domain in f. So let's put that on there. 0, 4, 8, 6, 3, 6, negative 1. 8, sorry. So each of my domains have a range. And now, if everything works, my domain of g, my range of g, should now be domain of f, range of f. So let's make sure that each of these y's has an x. Not -4. 4. Does a 4y have an x in my f? There it is. 4 has a 0. That one has a connection. It's good to go. 6. If I jump back up here, yep, I see a 6. It connects to a 3. Good to go. I look up here for my next one, which is another 6. I do not have another 6, so this one does not have an arrow, and it doesn't work for me. Let's double check that last one. Does this 8 have a counterpart in F? No, it does not. So I have lost 2 of my pieces that I need for this to be a true G of F. So while F of G did exist, G of F does not, because each range of G does not pair up with a range of F. So G of F does not exist. Doesn't work for us. I think that's the hardest part. The easiest way to check this is to just do some more examples of these. Give yourself 2 sets or find some online. They're pretty easy. Find an F, find a G, and then see if you can do the inverse the way that I just did with the tables. All right, last part. We can sometimes use composite functions to write formulas that involve 2 or more processes. In the end, we produce a new formula and potentially lessen the amount of calculations we need to do in the future. For example, the formula f of n equals n over 12 converts inches n to feet f. The formula m of f equals f over 5,280 converts feet to miles for m. Write a composite of functions that converts inches to miles. Well, we know we have to convert. Let me grab a different pen. There we go. Actually, let's write down our knowns first. We have f of n is equal to n over 12, and this one converts inches to feet. We then have m of f equal to f over 5,280, which converts feet to miles. We want a function, we don't know what it is yet, that converts inches to miles. If we look at this, it shows that we have to convert our inches first and then our miles. So, looking at our 2 functions that we have here, we're going to need to do f of n first and then m of f. So a function for this would be m of f of n. Or, using our new notation, m of f of n. Just like that. And I think this is easiest because it shows what order you have to do things in, and therefore what order you have to write your functions in. But that is personally just the way I like to do it. If you have a different way that works better for you, feel free to use that as well. All right, last example here. Susie wants to buy skates that are on sale for 30% off the original price, plus $5.75 sales tax. Express the price of the inline skates after the discount, and then express the price of the inline skates after the sales tax using function notation for both situations. Let x represent the price of the inline skates, p of x represent the price after the discount, and t of p represent the total price after sales tax. So I'm going to do this one way. There is a second way to do it with less operators, aka less addition and subtraction signs. And again, if you want to do it that way, totally fine. So let's first represent the price p of x after the discount. So if we get a 30% discount, that is the same thing as saying that we are essentially paying for the price of the skates minus 30% of the original price. Then, once we have done that, excuse me, we have to represent the total price after the sales tax. So the total price is going to be that P of X that we just had. That's the price after the discount, plus that 575. So plus, because it's a percent, we need to put it into a decimal form, 0.0575 of the price, because tax is based on what you pay. And that is our total price. However, because we know what P of X is, we can actually plug P of X into our T of P formula so that we have one less thing to calculate. And I could have done that up here as well, but with feet and miles, it seems pretty simple. So my T of P, once I've plugged back in P of X, I get X minus 0.30X plus 0.0575 times X minus 0.30X. And then I can simplify it down just to make it look a little bit nicer. I'm not going to do that for the sake of time. Some of you have said my videos get a little long-winded, so I'm going to let you do this one on your own. But that is just simple PEMDAS. So write a composition of functions to represent the final price of the inline skates. Well, because we took P of X first, and then we took T of P of X, another way of writing this would be T of P of X, or using our new notation, T of P of X. Again, however you want to write it, both of these are perfectly valid ways of writing it. You're probably going to see more of this one because it tends to simplify some of those parentheses, which can be a little confusing. All right. There's a lot there, so if you have any questions, please don't hesitate to let me know.